Okay, thanks. Whenever you're ready.
Right. So we were discussing the low energy EFT, and we said that at dimension 4, this is just the QCD and QED, and the cutoff is the electroweak scale, and the full flavor group is an accidental symmetry because QCD and QED are flavor diagonal. And then, for example, muon decay was a simple example of a process that probes directly higher dimensional operators because it's a stable particle in QCD and QED. It only decays through the weak interactions or BSM, if there is any. Okay, and so we used this the lifetime of the muon to infer the value of the cutoff, which in this case should be the electroweak scale, and we got the right value. Okay, of course, one assumes that C is 1. There were a few questions about this, but at the end, the main point is that whether you call the electroweak scale V or you call the electroweak scale MW, it's a matter of choice. They are both related. If you call it, if you want the electroweak scale to be MW, then of course you have a coupling there. So C is not 1, but if you call it the V, then C is 1. So you see there is an ambiguity here. Not that it's important because you know the whole thing analytically. So that's not really a problem. Okay, and then I also said that if you assume the standard model, then you can calculate this matching coefficient. If you do it at 3 level, you get something like this here. Okay, and then you can use the muon lifetime to extract either the vacuum expectation value of the Higgs or the Fermi constant, which are related by this expression here. Okay, and you get very precise measurements of these fundamental parameters. However, if there is new physics, then this extraction is not correct because then the matching coefficient contains extra contributions from, for example, heavy particles, and then this relation here is not true. And then if you use the muon decay to extract V or GF, you get a wrong result. And typically, what you get is something like this, where this is a BSM contribution. And in the most general case of the SMEFT, you can calculate this correction, and at 3 level is given by this simple example, this simple expression in terms of 4 Wilson coefficients of the SMEFT. Okay. Of course, if you have a UV model, you can calculate these Wilson coefficients in terms of the masses and the couplings in the UV theory. Okay, and I also said that this is something that you should do yourself. It's very easy and it's very instructive, and you can read it here if you want. Okay, so you see, this is a very similar example. This muon decay example in the low energy effective theory is completely analogous to the example of the proton decay in the standard model. Okay, it's a process that cannot happen at dimension 4, and therefore you can use it to infer what happens with higher dimensional operators. Okay, and the philosophy, the same philosophy applies to all flavor transitions, because in the low energy theory, dimension 4 operators cannot mediate any flavor transition because flavor is an accidental symmetry. Okay. In particular, besides proton decay in the case of the standard model or muon decay in case of QCD and QED, you have a huge number, or a large number of hadrons, which are the lightest hadrons with some specific flavor quantum numbers, and therefore they are stable in the sense in the same sense that the muon and the proton are stable in their own theories, okay? Meaning they are stable under QCD and QED. So low-lying hadrons are stable at dimension 4, okay? And so for the same reason, you want to study the decays of these low-lying hadrons because they give you access directly to this dimension 5 and 6 operators in the low energy effective theory. And so this gives you a direct probe of the electroweak physics and BSM physics, okay? Here I'm just writing some example of what I call low-lying hadrons. Kaons, okay, so pseudoscalar kaons are stable because they have strangeness and they are the lightest ones. So, and then you have also D mesons, which have charm, and they are the lightest ones. And then you have B mesons, which have beauty, and they are the lightest ones. And then you have B sub S mesons, which have both beauty and strangeness, and they are the lightest ones. Then you have lambda baryons, which are also containing Flavour quantum numbers, and they are the lightest baryons. So they're also the lightest ones with their own quantum numbers, and so on. So you have a bunch of particles that are stable at dimension 4 and whose lifetimes and branching ratios are going to be always proportional to a Wilson coefficient of dimension 5 or 6 in the low energy effective theory, and therefore you can use them to fix all these coefficients. Okay. This is a small exercise you can do, which is also an instructive thing. You go to the PDG, okay, to the particle listings, and you look at the table of mesons and baryons, okay, and then you have pions, you have kaons, you have rhos, you have all types of hadronic resonances and so on, and you can classify them always in 2 categories. There are the ones with large lifetimes of the order of 10 to the 12 GeV minus 1, okay, or 10 to the minus 12 seconds, okay. And then there are the other ones which have lifetimes which are smaller than about 10 to the minus 23. And there is a huge gap between those, okay. So all these mesons and baryons which are stable under QCD, they all have lifetimes of larger than 10 to the minus 12. And all the other ones that are not the lowest lying hadrons have lifetimes which are shorter than 10 to the 23. There is a huge gap between. So they are completely different from the point of view of physics of their lifetimes. Okay, and the reason is exactly this. The reason is that these lifetimes are always proportional to one of these Wilson coefficients, which is suppressed by the weak scale or some BSM scale. Okay, while these ones are just not suppressed at all, they decay under QCD. So I think you should go to the PDG, surf a little bit and look at all these lifetimes and convince yourself that in fact this is really an experimental fact. Okay, and this has 2 consequences which are important for BSM flavor physics. One is that it allows us to work with hadrons in a way that we can control. Okay, and you had the course on standard model flavor. If I actually followed her last lecture, and it was very good. And you did all these sum rules, and in all these sum rules, you have all these poles in the correlation functions. And the fact that these are poles is because you are assuming that these hadrons or mesons are stable. And then what you do is you know what they're defined by the fact that they are poles in the correlation function, and then you can calculate the residues, and then you can do all these dispersive dispersion relations, and then you can work out all these decay constants and form factors and all that. Okay, and this you can do because you can define the low-lying hadrons in this particular way. So I just write it here in a very simplistic way. So you have a Hamiltonian, you have the what you call the main part of the Hamiltonian, and then an interaction. And the interaction is only given by the dimension, the operators of dimension higher than 4. So this is QCD and QED, and here you have the operators of higher dimension. And since all these hadrons, for example, the B meson are stable under this H0, then this is a mass eigenstate of the H0 Hamiltonian. And then once you define the meson like this, you can start calculating corrections introducing this interaction Hamiltonian, okay? And then, for example, let me write it here, although this is just what IFA discussed. For example, if you consider a correlation function with two B meson currents, so something like this, of course, you have a T product and so on, but this will have an imaginary part that you obtain by including all possible intermediate states here. And you know that you have a pole, which is the B meson, and then you have a cut, which is like anything else, like B pi and all the other multi-particle states. And therefore, this object here has an analytic structure that looks like a pole and a cut, okay? And then you can just do dispersion relations. This gives you the residue of the pole, and then you can calculate, for example, this guy here, which is a decay constant, okay? And if you do like on some rules for B2 pi form factors, things like this, it's always based on the fact that you are defining the hadrons in this particular way. Okay, but this is not completely related to BSM, and you already had this course, so I'm not going to talk about this one. There is the second consequence, which I already mentioned, that you can look at weak decays, and since they are directly probing these higher dimensional operators, then you are directly probing a relation between electroweak and BSM physics, okay? And now I'm going to discuss, of course, you may say, okay, but this you're just testing electroweak. BSM could be there, could not be there. And now I'm going to try to argue that the electroweak standard model, which you already know because you had the standard model course, is so specific that typically you have suppressions that are not present in BSM models. And therefore, when you test these weak decays by measuring these dimension 6 operators, then you are accessing really very high energy scales, just because the electroweak scale is suppressed by additional mechanisms, which means that the effective scale of electroweak physics in this particular Flavour transitions is actually much higher, okay? So this brings me to this chapter, which is the last one, the last thing I will talk about. This is what I said. So studying transitions of hadron stables under QCD, we're directly probing.
So Javier,
yes.
Before you move on, there was a question in the chat.
Okay.
So the heavy hadrons with particular quark composition are not stable under QED and QCD because they can still decay to their light members with the same quark composition. Is that correct? Yes,
this is correct. I mean, for example, I can give you a simple example. So imagine you have some B star meson, okay? So some vector mesons with the quantum numbers of the B meson, and this can typically decay into a B and a pi, okay? And this is a strong decay, okay? And this typically happens very fast, and this is a strong decay. So this is not really telling you much about the weak interactions, okay?
Okay, so this is the reason that B star is not stable, right? And so I just needed to clarify.
Say again, I didn't hear this.
That was the reason that B star is not stable, right?
Yes.
Okay, so yeah.
Yes. Okay. Right now, so there is not just one B star. There are several, and then there is, for example, one B sub S star, which is actually stable because it decays into B sub S and gamma. This is a QED transition, so I would consider this as a stable meson. Okay, although this is a QED decay, so it's not really giving you much information, but this is a pole, and you typically use this. This you use in the when you parameterize the form factors. I think if I talked about this, you do the series expansion, so you have this pole and so on. So not all of these B stars are not stable. Some of them are very narrow and they consider to be poles. Yeah, but you want to study flavor transition, so you don't want your hadron to decay before you have the flavor transition. Okay, so in particular, if you have something like B star decay into B pi, this is not the flavor transition. This is not you don't need any dimension 6 operator to do this this transition, and therefore you're not gaining any information. Okay. All right. So yeah, so this is what I said. Now I give 3 examples. Okay, so I'm going to talk about 3 specific examples that I think that are enough to understand the whole point. I will be a bit explicit in the first example. In the second example, I will be less explicit. And in the third example, I will not be explicit at all, because I want you to understand that eventually you can do the calculations, but in order to understand what's going on, most of the times you don't need to actually perform the calculations. Okay. So the first example is the charge current transition B2Cl nu. Okay, so let's consider this this quark level transition, and we're going to assume that this happens via an operator of this type. Okay, so this is a 4 fermion operator, a semi-leptonic 4 fermion operator with a Wilson coefficient, and this mediates this transition in the obvious way. This is an operator, so this is an operator that is generated in the standard model. Okay, so we will have a standard model contribution here, but it can also receive contributions from beyond the standard model physics. There are actually 5 independent dimension 6 operators of this type. Okay, and so you can go to the papers and find these 5 operators, and you can do it in complete generality. But for this example, I will just consider this operator, and this will be enough. Okay. Of course, this is not what you observe. You don't observe a big quark decay into charm lepton neutrino. You observe the case of hadrons, and here I'm giving you some examples of hadron decays that are actually happening through this quark level transition. Okay, so for example, a B decaying into a D meson, a lepton neutrino, a B decaying into D star, a B sub S decaying into a D sub S star, a lambda B variant decaying into a lambda C L nu, an inclusive decay of a B meson decaying into a bunch of mesons and hadrons with charm. Okay, and so on. So all these observables, or all these modes that you can measure at experiments, they all happen through this B2Cl nu, and they will all receive contributions proportional to this coefficient C1. Okay, so you can use all these measurements to measure this coupling constant. Okay. Okay. So, and here, since I changed my notation, this is not C over lambda. This should be C1. Okay. Good. So now let's assume that we measure this coefficient, and then if we want to infer something from this, we need to know what the theory tells us about this, okay? So we would like to know what is C1 in the standard model and what is C1 in different BSM models, okay? And in order to do that, we need to do a matching calculation, okay? A matching calculation is going to fix the Wilson coefficient in the effective theory from the couplings in either an effective theory above or a BSM model above, okay? So I could match this coefficient to the SMEFT. This I could do. You can find it in papers. There are programs that actually give you this, this information and so on. What I will do is something simpler, which is just to consider the standard model by itself, but also a couple of one BSM model, a simple one that the matching is very simple to do. So let's consider, in order to do the matching, I just need to fix the coefficient in such a way that any amplitude is reproduced by the effective theory. Okay, if you achieve that, then you have the matching condition. So I don't have to worry about whether this is actually a physical transition of a meson or something like this. I can consider a partonic amplitude, P2Cl nu, and this partonic amplitude will be helpful for me in order to get the matching coefficient. Even if this is not a physical process, mathematically is good enough, okay? And much simpler, okay? So we want to require that the EFT amplitude is equal to the expanded full theory amplitude. Okay, we have to expand it because the EFT is an expansion in 1 over lambda. Okay, so at leading order, we first calculate the effective theory amplitude for B to C and nu. Okay, the leading order diagram is just this one here. Okay, very simple. So if you calculate this contribution, you get something like this, the typical I that you get always in the Feynman rules, the C1, which is just the, okay, so if you want, this is the Feynman rule for this vertex here, okay? And then you have this, this product of spinors. Okay, so this is the leading order calculation in the effective theory, which contains this operator. If you want to go beyond, you can consider gluons like this, you can consider photons like this, and you can complicate your life as much as you want. But to leading order, the calculation is as simple as this. And so the effective field theory amplitude is given by this expression here. Okay. Now let's calculate the amplitude in the standard model, also at leading order. And here you see the leading order contribution in the standard model, which is just given by the 3-level W exchange. Okay. And the important thing to notice here is that this momentum Q here in the propagator, okay, is a low energy momentum because you are considering a decay of a B quark. And so since Q is P of the B meson minus P of the charm, you have this expression here that Q squared is equal to P minus PB minus PC squared. And this is always going to be smaller than MB minus MC squared. And this is about what, 5GV squared. And this is much, much smaller than MW squared, which is the mass of this propagator. Okay, in fact, this is like 80 square, and this is 5 square. So you see that the hierarchy is obvious. So this means that when you calculate this diagram here, which you have, okay, you see the Feynman rule here is a G divided square root of 2 times VCB times gamma mu P left. And the Feynman rule here is G over square root of 2. There is no CKM element, but there is gamma mu P left. And then you have the propagator of the W. So at the end, you have C squared over 2, VCB, the product of spinors, and the propagator that I wrote here in the unitarity gauge. All gauges will give the same result at the end. I'm using the unitarity gauge in order to have the constants and so on. Okay. So the point is that since Q squared is much smaller than MW squared, I can expand this whole thing in Q squared over MW. And if you do that, it's a very simple expansion. This is what you get. Okay. So you plug it in, and this is your leading order standard model amplitude, which has the structure of a product of two spinor currents and a prefactor which contains VCB, G squared, and MW squared. Okay, so finally, the standard model amplitude is given by this expression here at the leading order. Okay, so this expression here. That's it, because the iPad sometimes is a bit slow. Okay, so now the only thing I have to do is to compare this expression, which is the expanded standard model amplitude, with this expression, which is the EFT amplitude. Okay, and this gives me an equation for C1, which is given by this expression here. Sorry about this, but the iPad is slower than me, so so this is why I have to wait a little bit. Okay, so this is the result for the matching coefficient C1 in the standard model. Okay, so what do we see here? We see that in fact it goes like 1 over the mass of the particle squared. There is some coupling in the numerator, and there is an additional suppression due to this CKM element VCB. And this suppression is of order lambda squared, because as you know, when you go from the second to the third generation, the CKM matrix has a lambda squared. Okay, lambda is the Cabibbo parameter, which is 0.22, so this is about 4%. Okay, now let's consider a BSM model where you have a new vector leptoquark. Okay, a leptoquark, so vector means it's a vector particle, leptoquark means it couples directly to a quark and a lepton. I'm giving you here the leptoquark Lagrangian. You have a term with a B transforming into a lepton, okay, with a vector particle U1, and then you have here a C transforming into an also by through an interaction with a U1. Of course, you have to consider the admission conjugate. This will be important because this is a B coming in. This is the term we want, but then we will need to have to do the admission conjugate here. Don't worry about that. And then you have a mass, a leptoquark mass, mu squared. Okay. This is not the UV complete model. Okay, you will have problems. You calculate loops with this Lagrangian, but for the sake of the trivial calculation that we're doing is good enough. So let's calculate now the amplitude using this U1 leptoquark. This is the leading order contribution to the B2C L nu amplitude. Notice that now this one and this one are exchanged compared to the contribution in the standard model, because this is a leptoquark. You have a B transforming into an L and a neutrino transforming into a C. Again, you have the same situation. This K momentum here is the momentum of the P minus the momentum of the lepton. This is again smaller than MB squared. So if MB squared is much smaller than the mass squared of the vector leptoquark, then you can do the same expansion that we did in the case of the standard model. Okay, so you work it out. It's very simple. You have a coupling here GB, you have a coupling here GC, and then you have here the propagator, and then here you have the product of the two spinor currents. There is a slight complication here, not very serious, but if you look at this, you have the first spin or current has a B and a lepton, and the other one has a C and a neutrino. So they're kind of crossed. It's not the same as we get in the standard model. In the standard model, we get the C, the B, and then the two lepton, the lepton and the neutrino. So it looks like we cannot compare both things trivially. We have to do something, and this something is just a First transformation. So I hope you are familiarized with First transformation. If not, you can. Yes. Okay. Sorry, I had some. Can you still hear me?
Yeah. Now we can hear you.
Yes, I had some problem. Okay. Right. So yeah, I was saying that you have to do this First transformation in which you switch. As you can see, you switch sorry, this one here and this one here. Okay, and then the only effect is a minus sign. This is the simple First transformation. There are more complicated ones, but you can also look this up in any. There is, by the way, I typically look this First transformation in something called the Core. You put this in Google. You put Core. You put compendium relations, and you get a paper of some Russians which have a lot of useful identities in quantum field theory. So there you can find all the First identities. You go to the index and there's First identities. You go there, you find things, and in particular you find this one here, including this minus sign. Okay, so taking into account this minus sign we cancel this minus sign, and at the end the amplitude for the U1 contribution to the amplitude will be given by this expression here, which can be directly related to the EFT amplitude. And this gives you this matching coefficient for the case of the U1 leptoquark. Okay, so combining everything, the coefficient C1 contains two contributions, the standard model contribution and the U1 contribution. And here, in order to understand how is the new physics going to affect my result, I'm factoring out the standard model part, and then I'm putting a 1 minus this term, which is the normalized leptoquark contribution. Okay. By the way, we will be doing very similar calculations in the tutorial. So you will have the chance to do similar calculations by yourself. Okay. Now, what does this mean? Okay, what does this mean? So imagine you measure some of these observables and extract an experimental value for C1. Okay, and imagine you do this with a relative experimental uncertainty, which I call sigma. Okay, and let's say that you find something which is consistent with this number here that you have calculated in the standard model. Okay, so this is what I'm saying. Imagine you measure this C1 and you get something like this, a value which is the standard model plus minus some experimental uncertainty. What can you conclude? Okay, so you can conclude something about this term here. Okay, you can conclude that this term cannot be higher than sigma. Okay, otherwise the result would not be consistent with the measurement. Okay, the calculation would not be consistent with the measurement. Okay, so you can conclude say to 68% confidence level, you can conclude that this is smaller than sigma. And this is going to give you some bound on the parameters of the new model, okay? In particular, from here, you can just write this expression here. The mass of the vector leptoquark will be larger than this, than MW multiplied by this square root here, which contains all the couplings and contains also this sigma. Let's do a very simple illustrative example. Imagine that all the couplings are of similar size. Okay, so these new couplings of the leptoquark to B and C are of the order of the electroweak coupling. Okay, we know that VCB is 4%, and assume that your experimental determination has a relative uncertainty of 10%, which is even larger than what is currently happening at LHC, for example. Okay, then by applying this bound here for MU1 leptoquark, we find that the mass of the leptoquark has to be larger than 20 times the mass of the W. So that's 2 TeV. Okay, so we are already probing the TeV scale with this 10% measurement of a flavor transition. Okay, that's pretty nice. Okay, and one of the key ingredients here is this 4% number. Let's see, this 4% number, because this 4% number, it doesn't appear in this model. Doesn't need to appear. Okay.
Sorry, I have one question.
Yes.
Yeah, so this inequality like GBGC and this product less than sigma. So the left hand side, this is only one term contributing to the coefficient C1 calculated for the U1 case. But there can be other terms as well, like as you wrote plus dot dot dot. So there can be like positive, negative terms as well. So when you
are wondering about this.
Yeah.
Wait for the iPad. You're wondering about these terms here.
Mm-hmm. So if
right,
have,
yes.
Yeah.
These
so
terms here are of different forms. So there are some things here which are just like standard model loop corrections, which you can calculate, no problem. And there are contributions from this expansion here. Let's wait here, which are completely irrelevant. Okay, much smaller than this 10%, not important. Okay.
Okay.
And then there are also some contributions from loop corrections to this thing, but this is also going to be much more suppressed with respect to this term here. You are very welcome to do the calculation like more precisely and with more corrections and so on. But at the end, in this particular example, you will find that this 2 TeV is not going to change very much. This conclusion here that you are probing the 2 TeV scale.
Okay, understood. Thanks.
But everything I say, you are welcome to calculate corrections, convince yourself of whatever might be missing, etc. Okay.
Can I ask a follow-up on that, Javier? 1 minute. So, of course, one could add another 4 fermion operator, right? That would lead to the final state. One could have like a flavor changing B2S or something, which no, I don't know what not B2S, but it's a if you go back to the diagram, we could have something else, right? Couldn't we?
So here you have, so if you're considering B2C new transitions, and you have 5 of these operators because they have different Dirac structure. Yeah. Yes.
Okay.
Yes. So yes.
But you couldn't have but we could have a charm to neutrino and charm to lepton and various permutations, right? As well. So I forget which one you actually chose in the end. What
You mean as the
peak
operator, or you're talking about the model?
the model. The
Ah,
model.
you're talking about the model.
So when you
This
have the
model here, no?
leptoquark, yeah.
Yeah, so you see this vector leptoquark has a specific charge, and so you cannot do lepton charm leptoquark, for example. That would be a different leptoquark.
Yeah.
You can do
Okay.
that, of course. That would be a different one. That's a different model, but you can consider that model. It will not change anything.
Except you could, but could you have both models simultaneously? I guess if we're allowing leptoquarks,
you can have two different leptoquarks if you want.
Yeah.
Yes, yes.
Well, I've seen these models actually. So people have tried to fit the data with various things, right?
Yes, yes, yes. If it doesn't work with one, you put another one. Yes.
Yeah, yeah. Okay, got it.
Yes. Yeah, everything can become more complicated.
Yeah, I'm not suggesting you do that now, but yeah, yeah, okay, fine.
Yeah,
fine.
but I believe that if you know this, then you can do also 2 and 3 and 4, and you can complicate your life as much as possible. But conceptually, there is nothing new. Let me go now to PSLL.
Hello.
Yes.
I had one question. Like, what was the motivation of choosing all the couplings of same order?
What is the motivation for this approximation?
Yes, yes.
Yes, there is no motivation. It's because if I don't do this, I cannot give you a number for the scale.
Okay, but if they are of different orders, then the scale will also change, right?
If you
ME1
change
will
this
change.
relation, then you change this number. You can try to. So if you really are interested in this model, you can look for different observables to try to separate these couplings also. Like for example, you can consider B to lepton, and then you have the U1 leptoquark, and here you have a GB. And then, for example, you can yeah, I mean, probably this is a too simple model, but if this leptoquark, for example, can decay into other things, which are not C neutrino, then you can separate these two couplings, and you have observables with different combinations of the couplings. And then by measuring that, you can actually separate the dependence. Maybe you can do a global fit to the 3 parameters of the model, which is GB, GC, and the mass. Okay, and then you can try to study all these things. This is just if you assume that the couplings of these leptoquarks are of the order of G, then this is what you get. If you assume that these couplings are very, very small, then the new physics contribution would be less and less important, and this means that this will go up, will go down. Okay.
Okay, but so I can always set my couplings in such a way that the MU1 is greater than the current energy reach of any collider, right? So then my model will be always correct, no matter what. Like, so how to?
Well, no,
test
because if you, so let's see. So this is M is larger than something. Of course, if M is super large, then this is also satisfied. So if you have a very, very heavy leptoquark, then there's no way you can see it. That's fine. But if you have a leptoquark, which is a TV scale, okay, then unless the couplings are for some reason very small, then you should be able to see it by looking at B2C transitions. Okay. Okay, so that's, yes. Okay, let's see a more extreme example, because this is actually the worst example in Flavour, the 3-level transition that we did B2C. This is the worst case. But there are better cases. This is, for example, B2SLL. This is a flavor changing neutral current. I think you have already discussed why these things appear only at loop level in the standard model. So this will be mediated by operators of this type. So BS bar lepton, okay, with different Dirac structures. Okay, I'm not going to do this in detail, okay, as I did for the B2C, just because I think you got the idea. In the standard model, you have to calculate this kind of loop diagrams. Okay, you have boxes and you have penguins, and this is actually not a very difficult. I had the intention of doing it chapter 6, but chapter 6 is not going to happen. So, but this you can find many places. You can even do it yourself. It's not difficult. But I can tell you what you get, because it's we know you already can know what ingredients appear when you do this calculation. You have 1, 2, 3, 4 weak couplings. Okay, in the same here, 1, 2, 3, 4 weak couplings. You have G to the 4. You know that this is a dimension 6 coefficient, so you know that this will be suppressed by MW squared. This is a loop process. So here you have a loop, here you have a loop. So when you calculate your loop, you get 1/4 pi squared by default. And then you have a CKM elements, because you have here, for example, VIB, VIS, and here you have the same thing, okay? 2 CKM elements that will look like this, and you have to sum over all the up-type quarks in the loop, okay? So when you do this calculation, you will get something like this times some function of some ratios of masses and so on. Okay, so this will be a function, normal function with order 1 numbers. Okay. Now let me be a bit specific with this. So if you do the counting of Cabibbo parameters, the U contribution to this CKM element is lambda 4th, which is much smaller than the contribution from the charm on the top, which is lambda squared. Then you also have Jim. So at the end, typically you only need to care about the top. This is not really important, but just to mention it. In the literature, what you find is something like this. You find these 2 operators, which are the vector left and the gamma mu, so vector axial to the leptons. Okay, these are 2 operators. We will find also this in the tutorial. And then typically you have the Wilson coefficients, and you have this thing factored out. And this is just something convenient when you do the matching in the standard model, but this is just a definition of what these coefficients are. And then just to argue about this very simple order of magnitude thing, I'm going to tell you what you get exactly when you do the calculation. Okay, you get that with this normalization, C9 and C10 are about 4 each. So order 1 numbers. Okay, and you see this GF is G squared over 2M. So this is exactly, this is this one with a G squared, but then you have this alpha over 4 pi, which contains another G squared and 4 pi squared, which is this 4 pi squared. And then you have VTS, VTB, which is this. So this very simple guess that we made here is exactly right. Okay, you only have to put a factor of 4, which is this factor of 4 from this standard model coefficients, which are calculated to 3 loop order. Okay, so this works extremely well, and it's enough for our purposes. Now, this is the standard model. Let's consider 2 possible 3-level models from new physics. Okay, one is a C prime model, so a new vector C particle, and another one is a scalar leptoquark. Okay, and here I'm writing the Lagrangian. So you have a B2S coupling with the Z prime. You have also the Z prime with the leptons. Sorry, here we have primes here, and we have prime here. Okay, And the leptoquark is very similar to the U1 leptoquark, but it's a scalar leptoquark. Okay, so you have a B coupling to the lepton through the scalar, and an S coupling to the lepton and the scalar. And then you have masses for both the C primes and the Z. And I'm not considering this together, but just as two separate models. But of course, you can put them together if you want. Now, you could do the calculation in the same way we did before, etc., etc. It's not needed. You know what you're going to get. The coefficient, the Wilson coefficient, any of these Wilson coefficients of any of these operators will either be 0 because of the structure of, wait, I have to wait. Yes, so these Wilson coefficients, they will either be 0 because of the structure, but the ones that will not be 0 will be given by expressions such as this one and this one. Okay, this is just the same calculation we did in the B to C case. You do it here, you know what you get. You get things like this, okay? 2 couplings and the mass of the particle. 2 couplings and the mass of the particle, okay? We can do the same exercise as we did before. So let's say that you measure this coefficient by measuring all these modes, and then you have a relative experimental uncertainty of 10% on these Wilson coefficients. Let's also assume for simplicity that all these couplings are similar to the weak coupling, okay? And then we find, if you do the exercise, that the masses of this Z prime or scalar leptoquark are going to be larger than this thing here, which if you plug in the numbers, you get 20 TeV. Okay, so we went from 2 TeV to 20 TeV. So now we are probing tens of TeV. And why is this now much larger than the 2 TeV before? Well, because you have additional suppressions. You have the loop, you have the loop, you have the CKM, you have a fourth coupling here instead of 2, etc. Okay, so the fact that these processes in the standard model happen at the one loop level, okay, mean that if you have a generic new physics model that doesn't have these particular suppressions, then you will be able to probe much higher scales. Okay, and yes, we will consider specific bounds on C10 and on the C prime and leptoquark model in the exercise session by looking at the B sub S to mu mu branching ratio. So you will be able to do this in detail and to convince yourself that this is what you get. Okay, so let me see. There is a comment here. This is the end of the lecture. Just a very brief comment. This is an interesting example by itself because these BSLL modes now contain some anomalies called neutral current B anomalies. So now we can, if these anomalies are really due to new physics, then you can infer non-zero values for these combinations as we did. So we're not just looking at bounds, but now we are talking about the real measurements of these parameters of new models. However, once you commit to one of these models, you have to be careful that these models will not give you contributions to processes that do not deviate from the standard model. Okay, so for example, you have an observable which is called delta S, which is related to the mixing of B sub S mesons. So this quark level process here, B S bar going to S B bar. And this is well measured, well predicted, and is consistent with the standard model. And then if you want to assume that the C prime of this type gives you the deviations in B to SLL, okay, you have to be sure that the model parameters that you extract are not in conflict with this measurement here. Let's see, here, okay. However, the problem is that the C prime contributes to this process at tree level, as you can see here. And so this gives a very large contribution to delta MS and is actually excluded mostly. Okay. The leptoquark, however, it's interesting because it only contributes to B2S mixing at one loop. Okay, because since the leptoquark always require a lepton and the BS bar to SP bar process contains no leptons, the only thing you can do it is at one loop. So that's why typically a leptoquark is preferred over a C prime when you want to explain these B2S LL anomalies, because you can avoid a strong bound coming from this mixing of p mesons. Okay, so finally, as a third example, as you can see, I'm giving less and less details. If you look at neutral meson mixing, such as, for example, this B sub S mixing I just talked about, this gives a super strong bounds on tree-level new physics. So you can do the same exercise, put the C prime, calculate this thing here, do the exercise of looking at the measurements of B sub S mixing, all sort of things I'm not going to talk about. You can see the details, for example, in this paper here. And here you can find just the bounds on the new physics scale, on the effective new physics scale that you get from all these Wilson coefficients of all these operators that contribute to PP bar mixing, KK bar mixing, DD bar mixing, and so on. And you see that depending on what you assume for the couplings, for example, in the most general case, where the couplings are order 1 and there is no suppression of the tree-level new physics, you get an effective scale which is 10 to the 12 GeV, that's 10 to the 9 TeV, that's very, very high. If you assume that the same suppression as in the standard model happens in the new physics, you get 100 TeV, which is also quite high. Okay, so this would be like another example where the flavor really works very well to probe very high energy scales. And okay, I think it's time. This is just the summary of the whole thing. So maybe if I have a couple of minutes, I can just remind you. I have a few minutes, no? Or should I stop here?
No, you do, because the tutorial sessions were all 90 minutes.
Anyway. Right. Yes, I have 30 more minutes. That's fantastic. Okay, so yes. I will be able to show you also some other things. Perfect. Okay. Yes, so let me go now to the summary. So the standard model is an EFT because you don't need this renormalizability axiom. Okay, and this is not a problem because you have something called a power counting. And we did this exercise with this diagram of dimension 8. You need to renormalize, but then if you don't put it because it's 1 over lambda to the 4th, then everything works. You can renormalize, etc. The fact that the effective scale of these operators is much larger than the electroweak scale, this explains why the standard model works so well, and explain why the renormalizability axiom actually is looks like a true thing, but it's not needed. And then the best tests of these higher dimensional operators are the ones that are the processes that break accidental symmetries, because these symmetries are symmetries of the dimension 4 Lagrangian, but not of the higher dimensional operators. So all these processes like proton decay or neutrino masses are directly probing these dimension 6 operators. Okay, so you have this Lagrangian, and then you want to measure these coefficients of these higher dimensional operators to learn about physics beyond the standard model. This is the first point. The second point is flavor. Flavor is an accidental symmetry of the low energy theory at energies much lower than the electroweak scale, and therefore is the right sort of processes you need to look at if you want to test the dimension 6 operators of the low energy AFT. In this case, this is not directly related to BSM physics, also contributes electroweak physics, okay? But it's interesting to test the electroweak standard model and compare it with possible BSM contributions. So this suggests to look for weak decays and mixing of stable hadrons. Okay. You can also look at leptons. This is equally interesting. So tau decays also give you a lot of information about weak scale physics. And then the fact that the electroweak physics is very specific, has a very specific flavor structure, has many implications. One of them is flavor changing neutral currents only appear at one loop. And this means that any new physics model which has no such suppression will typically compete very strongly with the electroweak contribution. And this means by looking at these transitions, we are able to probe very high effective scales, much larger than the electroweak scale. So in the case of charge currents, we saw that the effective scale, not even the effective scale, because I was putting the couplings equal to the standard model. So the effective scale would be even larger, but we're talking about several TeV. In the case of MCFCs, we were talking about tens of TeVs. In fact, the current B anomalies point towards a scale of about 35 TeV. Okay, and in the case of neutral meson mixings, where the theory is much more precise and the experiments are much more precise, in generic case, that you cannot probe directly, you can only probe indirectly. So this is a very powerful tool. Okay. So I hope this convinces you that the Flavour is a very powerful tool to probe high energy scales and to probe BSM models. There is also a second message here. There is a global research program that is going on right now, which is measuring the coefficients of the higher dimensional operators in the EFT, and consists in 3 steps. First, write your relevant EFT. Okay, the dimension 4 part will contain some dimension 4 couplings, and then you have some higher dimensional operators with some Wilson coefficients which are suppressed by some scale. You choose a suitable set of observables to test all these Wilson coefficients. You calculate the observables in terms of these couplings and these Wilson coefficients. Okay, this is difficult. I didn't talk about this, but IFA talked about calculations of observables, I think, and this is a difficult thing. I mean, you have to do higher order calculations in perturbative QCD. You have to calculate non-perturbative matrix elements. It's a mess. But most of the times you can do a reasonable job here. So you calculate all these observables in terms of all these couplings. You measure these observables experimentally, or you tell your experimental friends to do that. Most of the time you don't need to ask them, they do that themselves. And then you do a fit to determine all these free couplings. And it's important to mention that we are not only talking about the Wilson coefficients, we're also talking about the parameters of the dimension 4 operators. So if you're talking about the SMEFT, we're not only talking about measuring the Wilson coefficients of the SMEFT, but we are also talking about measuring the parameters of the standard model. Okay, and this is also a very important task, and both things are most of the time related. I mean, you probably heard about this new measurement of the W mass by CDF. There is a huge difference with respect to the global fit, and this may point towards the fact that the the extractions of these parameters are affected by possible BSM physics. And then I showed you an example with the CKM fit, no? That if there is new physics, then the determinations will not match one another. Okay, so typically in the optimal case, you would need to do a global fit to determine everything simultaneously. In practice, since you have very precise measurements that allow you to measure these standard model parameters, you can do that first, and then you can use different observables to access this information. You can do as you wish. And once you have determined these coefficients, you can compare them to models, and you can try to conclude which models are in agreement or are not in agreement, which models are excluded, which models are not excluded, and so on. And I say half of the HEP community works on some part of this program, but this might be an underestimation. Maybe it's more than half. Okay, so this is a global program, and most of the people I know are doing one thing or the other in this direction. Okay, do we have any questions?
Nothing here in the chat.
Okay. So now, since I have more time than this, I forgot about this 1 hour and a half. So I have 20 minutes, and I think it's interesting to show you. So I have two things I wanted to show you. One is a simple one-loop computation of a matching condition that can be instructive. And the other thing is a Mathematica notebook where you can, if you have access to this software, there is a package that you can use to do all kinds of things with SMEFT and left operators and things like this. I think I will, since I have the iPad already connected, let me do first this one loop calculation, and then if there is time, I can show you this notebook. Okay, so I'm going to do it directly here. So let me add a couple of pages. Okay, so I'm going to consider the same scalar leptoquark that we considered before. So I'm going to consider the Lagrangian, where you have this B to lepton phi. Okay, so let me see, like this, and also an interaction of the type lepton S quark phi. Okay, this is the same Lagrangian that I wrote before for the BSLL case. And I'm going to consider a diagram that I already showed you, which is the contribution of this leptoquark to this process B to S bar to B bar, okay, phi, and here leptons. Okay, so this would be a contribution to the BB bar mix, B sub S mixing amplitude. Okay, which is, as I told you, a very strong constraint. And so it would be interesting to know what this model gives for this contribution. Okay, the reason why I want to do this is because if you remember when we did the matching calculations, we were typically having something like this with phi, and then we were saying this is a PV, and this is some other momentum, and this is momentum here K in the propagator, and we have that K squared is of the order of MB squared, and then since the propagator will have a K squared minus M phi squared, this is more or less minus I over M phi squared plus order MB squared divided by M phi squared, which is a very small number. Okay, but now, of course, you may, so let me erase this. You may say, okay, but what is going on in this loop diagram? Because what can I say about this? What can I say about, I have a loop momentum here, which I will call K. And so what can I say about this propagator that I have here for the phi, 1 over K squared minus M phi squared? Can I do the expansion here? Because I'm integrating over loop momentum. So can I do this expansion? Okay. So this is the question you may ask. Okay. So I'm going to tell you how to do it. And you're going to see that is very simple. So if I want to write the Feynman integral for this contribution, okay, I will get the following. I will get a IA equals to some integral, the dimensions, in case this is finite, so I will not need to do it in the dimensions, but in general, let me just write it like this. And then you can calculate these two Fermi traces. You have a P right here, you have a P left here, you have a P right here, you have a P left. Okay, so you have a product of spinors, you have a P right, you have the lepton propagator. I will put the masses to 0, but if not, it doesn't matter, they go away because of these projectors. This one and this one will tell you that the mass term will cancel. So here you will have, I will put here the momentum here, it will be K plus PB, where PB is this momentum. Let me do it a bit like this. Okay, and here I will have K plus PB, P left. So this is spinor product multiplied by this fermion line here. So that's P right K slash plus PS bar, because this this momentum here is going to be, this momentum here is going to be, so let me put it like this. This is PS bar, and so this is going to be K plus PS. Okay, so that's why I have here this, and then P left. Okay, and then here I will have 4 propagators. I will have the propagator K plus PB squared minus M lepton squared. I will have the other fermion propagator K plus PS bar squared minus M lepton squared. Okay, and then I will have also 2 leptoquark propagators. One I can assign a momentum K, and the other one I can assign a momentum K plus Q, where Q is PB minus PS. Okay, so you just can work these kinematics by yourself. So here in the denominator, I have K squared minus M phi squared and k plus q squared minus m phi squared. Okay, right, so this is what you get. And now you can, of course, try to do the integral completely, but it's not needed. What we're going to do is we're going to separate this integral in two regions. Okay, we're going to do the integral in two regions. First, we're going to do the region of integration where k is of order m phi squared. And then we're going to do the region, well, so k of order or larger, okay? And then the region k, which is of order mb, or a small mass, okay? mb. Okay, in this first region, what I can do is k plus pb, for example, squared minus ml squared, which is the first propagator we have, is going to be about k squared, because this is of order m phi squared. I can neglect the other terms, which will be suppressed by mb over m phi squared. The same for k plus ps squared minus m squared will be k squared plus blah, 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 blah. Okay. And k plus q squared minus m phi squared will be k squared minus m phi squared plus blah, 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 blah. Okay. Let me put this region down below. Okay. All right. So if I do this, these replacements, I have that this region of integration will give me the numerator, which I can also expand, p right, k slash, p left, cross, p right, k slash, p left, divided by k to the fourth times k squared minus m phi squared squared, plus things of order mb squared divided by m phi squared. These are all the things that I have when I'm doing the expansion. This can be done exactly, I mean, but this is the truth. All these things are what I have neglected here. Okay, so this is always the case if the integral I'm doing is on the region of k of the order of m phi squared or larger. Okay, this integral is very easy to do because it only depends on one scale, only depends on n phi squared. Okay, and in fact, this, by the way, I didn't write the couplings here, but it's not really an important thing. I mean, here I have this coupling here. So let me see, this coupling here, this one, and this one. So here I will have to put GB squared and GS squared. Okay, I'm going to call this big G just for simplicity. So here we have a big G. Okay, and this is going to be G divided by m phi squared This is because of the dimensions. This only depends, this integral can only depend on M5. There is no other mass scale in this integral here. And if you count, you have here 4 powers of moment, you have here 8 powers of momentum. And here you have 4 in the numerator and 2 in the numerator. So 6 in the numerator, 8 in the denominator. So this necessarily has an M5 squared in the denominator. Okay? Times some function, but what can you have? This is a finite integral. So you don't have mu, you don't have the renormalization scale. Otherwise you would have log of mu over M5 or something like this. But this is finite and only depends on one mass. So this is times an order 1 number, which you can calculate. Okay? Plus order mb squared divided by m5 squared. Okay? Now, let's look at this region here, this other region of integration. In this region of integration, what can I do? I can do k squared minus m5 squared equals minus m5 squared plus order mb squared divided by m5 squared, and k plus p, plus q, I had k plus q minus, so squared, phi squared. I'm just copying these terms here and expanding them, okay? So this now is going to be minus m5 squared plus order mb squared divided by m5 squared, okay? Remember that k is of order mb squared and q is also of order mb squared, okay? So I can do this expansion. And then this is even simpler than before, because now these two propagators just give me 1 over m5 to the 4th. And then the rest is just some integral that does not involve at all the mass m5, okay? I'm not saying it's an easy integral. It depends on the mb, m-lepton, and so on, but I don't care because this region, in this region, I will have, so let's see, let me call this region 1, and let me call this region 2. This region 2 will be the couplings m5 to the 4th. In order to fix the dimensions, I have something like mb squared, okay, times something that does not depend on m5 plus blah, 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 okay? So now you see that comparing these two contributions, this is of order 1 over m5 squared, and this is suppressed by an additional contribution here. So this region will not contribute to the order in the EFT that we are working in. So I only need to consider this region here, and the calculation is, as you can see, very simple, because it only depends on one mass scale, which is the heavy scale. This is the integral that contributes to the matching coefficient. And the matching coefficient is exactly of the form you expect. Okay? I wanted to do this, this simple example of a one-loop matching calculation in order to teach you about the regions and about the scalings and how you do all these calculations and how it works. So now it's true that my time is up, but I'm happy with what I covered. So if there are any questions, I can answer them.
Hello. Why you are not considering the region between MB and M5?
Yes, good question. So you mean the region in between, no?
Yes, because the loop integral runs from 0 to infinity, right?
Yes. All right, good. So this region, you would consider the region where k is much smaller than m5 squared and much larger than the low scales mb squared. Okay, so this intermediate region, you can do it. You can, and this is a good exercise. So take this region, expand, okay, for m, so it's much smaller than m5, it's much larger than the low energy scales, and what you will find is a scaleless integral, an integral which contains no scales. Okay, it contains no low scales because of the reason you don't have low scales here, and it will contain no m5 because the m5 will be factorized out of the integral. So you get a loop integral with no scales, with no heavy masses and with no light masses. And in dimensional regularization, these integrals are 0. Okay, so you may consider this intermediate region, but it will give a 0 contribution. Okay. I think I can, if you are interested in understanding better these regions, I want to give you a reference that contains a discussion at the very beginning of this method of regions, which is a lecture notes. It's in the archive. I don't know the archive name, but lecture notes on soft collinear effective theory by Becher, Ferroglia, and I don't remember who else, but it's very easy to find. I think this is probably 2014, more or less, something like this, I believe. It has a very, very simple discussion, starting with a one-dimensional integral, how you break them by regions, how you can test that in fact the full integral coincides with the sum of all the regions, etc., etc. So if you have any interest in this subject, I think is very interesting for you to look at this introduction in this lecture notes.
Okay, thank you.
I recommend it. So for everyone, please, if you have some interest in this subject, please have a look at this first chapter of this lecture notes. 410, yes. So yes, thank you. So this is the archive number 1410. Let me write it here. 1410. 1892. Any more questions? Maybe I can just put it here. 1410, 1892. Exactly. So this is the one, Introduction to Soft Collinear Effective Theory. And then, of course, this is a much wider topic, but there is here a strategy of regions, chapter 2, a simple example. And here you can see this integral in 2.1, which you can solve exactly by simple integration, but then you can decompose in regions. And this chapter 2.1 is very instructive, and I think you should everyone should read this chapter. It's very simple to understand and very very instructive. Mm-hmm.
Okay. So I don't see anything else. So we'll start again at in 25 minutes. So it's a short break now, and Aritra will be leading the tutorial. Are you going to be around, Javier, or are you?
I hope so. I hope so. I have to see. So I have something else at some point, but I will do my best to be as much as possible. Yeah.
So yeah, because then there's an hour for the first part, and then Karim will give a lecture, and then it can pick up again after that. Mm-hmm. So yeah, we'll take it from there. But thank you very much, Javier, and